Example 5 is similar to example 4 in a way because in example 5 we're going to be tossing a coin and recording whether it's going to land heads or tails. And example 4 basically had an 8-bit string and the bits could either be 0 or 1. So heads or tails, 0, 1, it's pretty much the same thing, okay? Now, in example 5, we're looking for how many ways can at least 8 heads be obtained. And we're tossing the coin 10 times. So there are 10 tosses, and we basically want to figure out how many ways can at least 8 heads be obtained. Well, that just means that you can have 8 heads or 9 heads or 10 heads, okay? So we're going to break the problem into basically 3 different sets and count each one of the sets separately, okay? Okay, so again, when you end up with 8 heads on a toss, that's kind of similar to the 8-bit string that we did earlier, except, you know, this time you have to select where the 8 heads go. So you can select them 1, 2, 3, 4, 5, 6, 7, 8, and the other 2 will automatically become tails, for example, okay? So how many ways can that be done? Well, you're selecting where the 8 heads go, and you have 10 possibilities for, 10 tosses, basically. What about the 9 heads? Again, it's kind of similar. You're going to figure out where the 10, out of the 10 ones, which ones were the heads, and you want 9 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and the last remaining one will automatically be tails. So what did I do? I had to pick 9 out of the 10 choices and put heads in all of them. And then finally, the last choice, I have to make all of them heads, so I don't get to pick. It's 10 out of 10. You have to choose 10 heads out of 10. And so that's basically one possibility. Okay, so we're going to calculate each one of those separately, and keep in mind that these sets are disjoint. So sets are disjoint. In other terms, a toss where you have 8 heads is different than one where you had 9 heads. It cannot be mistaken for a toss of 9 heads, or if you had all heads, 10 of them, then that cannot be mistaken for, a game where you had 8 heads. So the sets are disjoint, which means I'm going to calculate each of the numbers separately. And once I have the separate values, I'll go ahead and add them up and get the total that I'm looking for. So the numbers were 45, 10, and 1, and so the total is going to be pretty much 56. Let's go ahead and write that down. So there we go. Saying that we have at least 8 heads means that we have exactly 8 heads, or exactly 9 heads, or exactly 10 heads, and the total is going to be 56. Okay. So now the question is, what's the probability of obtaining at least 8 heads? So the probability that we end up with a game that has at least 8 heads. So according to the formula that we learned previously, it's going to be a fraction with 56 on the numerator, because that's how many games you can have at least 8 heads, divided by the total number of possible things that could happen. How many possible games can there be? Okay, so total number of choices. Now remember that in these games, you've got 2 possible scenarios for each toss. You can either have heads or tails, basically, right? So tails or heads, so that's 2 of them for the first toss. And then for the second toss, it's basically, again, heads or tails, so that's 2 of them. And you're doing that 10 times in a row. So how many possible games are there? There are possibly 2 to the power of 10 possible games, because 2 times 2 times 2, 10 times in a row, okay? And so the total is going to be 56 divided by 2 to the power of 10. And again, I'm going to make it into a decimal and then round it. So 5.47% chance, basically. So that's the probability of playing a game and seeing at the end at least 8 heads showing up. Again, the percentage or the probability is very small, because typically speaking, you're not going to get 10 heads in a row. That's really ridiculous. Or 9 heads in total. I mean, you'd have probably an unfair coin if that was happening. So that's kind of the reason why the percentage here is very tiny at the end.